Brandon already told me that I'm from the Netherlands. I kind of would like you to guess it, but he already gave the secret away. Maybe you can hear from my accent indeed. I'm from the Netherlands. I hope my accent is not as bad as my Prime Minister's one, because that's really terrible. But what we're going to talk about, or I'm going to talk about today, is kind of the follow-up of what we've discussed this morning. Like you talked about building stuff, releasing stuff in the environment, but I'm more into, okay, then what if it's run in production? What challenges do you face over then? So I'm going to talk a little bit about a modern look at root cause analysis, not necessarily only in the cloud environment, but we see some changes in that approach of root cause analysis taking place because the movement to microservices and cloud environments. So again, a Dutch company founded in 2015. We had a mission to create a zero downtime a reality. The funny thing is actually, it kind of get catched up because by the introduction of microservices and cloud environments, there is not many downtime anymore. So the traditional look at monitoring availability, for example, is kind of moving to some different approach. So 3 topics that new practice I'm going to talk about a little bit in a second requires to revisit root cause analysis. However, issues will still be there, and then we need to treat them differently. And then I'll go into how do we see the world of observability and how we change that observability practice. So the first topic. Actually, Google introduced site reliability engineering. I kind of assume you're all a little bit familiar with them, but that's really about changing the perspective of how you do your operations. So instead of looking at availability, really looking more something like we call reliability. And availability is not the same as reliability. However, they're kind of closely matched. It's not the same, again, like I say. So Jerry already mentioned this morning, you have to be focused on your end customer. Focus on what they experience. If you look, for example, what we did before, looking at the availability of a server, who cares? You should care if the availability of the server is actually impacting some customer experience. But in the end, reliability is service-oriented. Oh, then something goes wrong here. I think I pressed the off button. Here we go.
Here's the down button.
Yeah.
There we go. Yep.
So, again, really looking at service to what internal customers, that's really what matters. So not about availability and monitoring and CPU utilization and all that crap. It's really like, what is your end customer experiencing? That does really matter. So what's relevant to why do you make a difference between reliability and the system and the availability? Well, systems typically are the whole, and on top of those systems, that's where your service runs, and that's what actually you could call it your digital product, or your core value proposition is providing value to the end customer. Low system availability typically results in low service reliability, but the opposite is not necessarily true, right? I mean, high availability does not necessarily mean you have high reliability. A very nice example of that was with one of my customers. They are in the streaming television services in Germany. They had a problem in the environment. The system was completely available, but when certain customers selected CNN, the actual channel they got was Eurosport. So it's available, right? But it's not reliable because I, as an end customer, expect CNN to see on my television. So again, customers care more about the result. It has to serve their purpose. Expectations about this reliability can actually be measured. We call that service level indicators. I'll talk a little bit more about them in a second. Service level indicators are actually the things that you kind of have to establish to kind of be able to measure what your end customer is experiencing. And it sounds really easy, but sometimes it is really difficult. Like sometimes you see, I want to measure my CPU utilization or my memory utilization. Does that really reflect what your end customer is experiencing? I don't think so, really. So we really have to establish some measurements, and ideally you do that in conjunction with your end user. You have to understand when are they happy and when are they not happy. Just assuming things is not the right way to go, in my opinion. That's also really tied together, like what type of service are you providing? If I provided something like Facebook that a lot of young people are using, a response time of 100 milliseconds might be not good enough. If I have a website for people like me, elderly people, 2 seconds to me is fine enough for me. So you really have to understand what your end user is expecting from your service and when they are happy or not happy. And then when you have established those service level indicators you're going to measure, you actually kind of look at the service level objectives. That's kind of the expectations. What should it be? Talked about availability before. Things like 99.9% availability might be an SLI, but bear in mind 99.9% means only 43% downtime in a month. So is that achievable? Is that acceptable to your end customers? So let's talk a little bit about those definitions. Service level indicator, again, these are the things that you measure that is representing the experience of your end customer. Then I already talked about this before. The objective is what you are achieving to accomplish in that one. And you have to measure that as well. And I'm not going to cover the full SRE practices, but typically this also incorporates the terminology like error budgets, where if you, that 43 minutes, for example, I talked about before, if you have to spend, let's say, 30 minutes to solve the problem, in that month you have only 30 minutes error budget left. Means if you spend the next 30 minutes on that error budget, you don't deploy and you don't change anything in the environment anymore. It's a methodology of kind of keeping the balance between fast deployment and value add to the customer, but also preventing problems to happen too often. And then the service level agreement, typical a contract between, not always applicable by the way, but a contract between the end user and the company. And typically the service level agreement is lower than the service level objective. So you might establish a service level objective again from 89.9% availability. Then you might establish that service level agreement just 97%. So these are kind of the introduction to that service level site reliability engineering. Those service levels indicators, we mostly use availability and latency because they tell something about the end user's experience. But you could also think for some other ones like coverage or correctness. The one example I just gave you with that video provider, it was available, it was presented within, I don't know, 100 milliseconds, but it was the wrong content. So correctness could also be a measurement that you would look at. Or things like freshness. If you're in batch processing technologies, you might want to look at how fresh is the data that I'm processing. Maybe it's not relevant anymore, it's outdated. Again, it doesn't really matter which one you pick, but you have to pick some that actually reflects what your end customer is experiencing. And of course, Google also gave us the 4 golden signals, like these are the most commonly used things that you could measure. Latency, like response times, very obvious, obviously. You could look at the traffic, like how many web server requests do I have, how many people are on my Ryanair website in an hourly based, etc. You can look at the error rate, like how many HTTP 500 errors occur, or 404, or whatever type of errors, and look at the requests in that perception. And last but not least, the things called saturation. Saturation is not just one measurement, and typically it's mostly related to infrastructure level things like CPU utilization, I/O, memory utilization, etc., etc. So, who cares about this? Because with this in mind, I already told you, issues will still be there. Treat them differently. What do I mean with that? Well, before we had traditional monitoring, we actually only looked at symptoms, like, yeah, my CPU is at 100%, or my web server is down. With observability, we want to look not only at the symptoms, but also at the causes to that problem. And at the bottom you see some examples where you see a symptom, responses are slow, the cause actually appears to be CPUs are overloaded. And I will come back to this one because I do not really agree. That CPU is overloaded does not explain why it's overloaded. Maybe there's a cause that actually caused that CPU to be overloaded, right? And I'll talk about that a little later because I think, and we already discussed this a lot of times this morning, changes are extremely important in this respect. When you do effective troubleshooting, again, it is again from Google Site Reliability Engineering best practices. A problem report is initiated, and then the triage starts. You're going to examine the problem, diagnose, you're going to test and treat, and if that works, it's cured. However, the first step, the triage, that's a very important one because I did not talk about root cause analysis yet, right? And the title of my slide was root cause analysis. I'll be there in a couple of seconds, don't worry. Because when you do the triage, your instinct will tell you to find the root cause as quickly as possible. However, you should ignore that instinct. The first thing you should be caring about, how do I get my service back running as soon as possible again? And even if that means that some manual intervention is involved, somebody has to reboot a process every minute, I really don't care. I want my service to be back online as soon as possible. And only then you start worrying about the root cause of the problem. Kind of with the blameless postmortems you already talked about, right? That's where your team really starts to sit down together and see, okay, why did it happen? How can we prevent it from happening again in the future? And what was the actual root cause? But again, in the traditional monitoring world, we always said, oh, something goes wrong. I need to understand what the cause was. It doesn't really matter at the first. Sometimes it does, right? Sometimes you just can't bring the service back online without actually understanding the root cause. So that brings me to the next topic, the observability practice. In the modern world, where we see that increasing rate of change, we talked about it this morning a lot already, increasing growing complexity, more microservices got introduced, more granular services are actually deployed, we got virtualization, we got cloud involved, hybrid environments, and these two together actually increases the challenges to keep up with that change, to understand what happened, how they are impacting one another, and how things actually are related. And I particularly like this one at the bottom, that from Digital Enterprise Journal report, 76% of all problems are caused by a change. And think about that. Most observability and monitoring tools look at symptoms. They see CPU utilization is high, response time is high, but they typically don't take changes into consideration. You should figure that out going back to your change, your CI/CD tooling pipeline tools, etc., like that. And talking about change again, I heard quite some interesting numbers, like 5 releases a day. Think about this one. Google is deploying in their environment new stuff every 11 seconds. That's how. I mean, every 11 seconds they deploy some new stuff. That's 300 new things per hour. That's how do you cope with such an increasing rate of change? Because the classic observability, like all the vendors in the world right now pretty much, they talk about observability is about metrics, logs and traces. These 3 ingredients should be giving me enough information to actually establish the root cause. Well, I think I look a little bit differently to that, because with our observability maturity model, we kind of distinguished 4 levels of observability maturity. The first level is monitoring. Again, looking at symptoms, measuring response times, measuring CPU utilization, etc., active users per minute. Observability, the aim of observability is also to add the causes to that. And for that, most of the used technologies for that is adding tracing technology. So you understand how the user is flowing to the environment, what the average latency is, how the connections are, etc. And this is actually the promise that all vendors, and I'll be fairly honest, including StackState, a couple of years, promised to the market, AI Ops. That will solve all your problems. You start smiling, Jerry, because I think you know about this. In reality, we all miserably failed in this one, because also in a report from another analyst bureau, they said 96% of all AI and ML initiatives miserably failed. And that's humongous, right? Why is that? Because the lack is in the middle. The level 3 is the causal observability. And I'll come back to that later. Causal means having a real understanding how everything is connected to one another. What is talking to what is interacting with what. And with only looking at traces, you get a limited picture of that, but there's still some components outside that visibility of those technologies itself. And coming back to AI and ML, I talk to a lot of prospects, and again, they say, I need AI. And they say, no, is that a goal, or should it be a mean to something? And I always say, I'd rather have a not so well algorithm be applied to a very good subset of data than a very good algorithm applied to a bad subset of data. And this is where we believe, or I believe, that causal observability is actually the place where we should go, actually have that in place before we actually can move to that world. Because if you look at the observability data challenge, we think it's just a data challenge. The data is there typically. You monitor a lot of things, you have dozens of tools in place already, but when you see the more dynamic environments like all the microservices, they change continuously, new containers spin up, they go, they come, connections are changed, load balance are routing the traffic to different components. And then you see the telemetry silos, because in your total environment, you typically have a lot of different monitoring tools or observability tools. You've got cloud monitoring, like AWS CloudWatch or Microsoft Azure Monitor. You have some server monitoring in place, maybe like Prometheus or Nagios or Zabbix, whatever. You've got some network monitoring, you've got some data lakes, You've got some APM technologies in place as well that are looking at the tracing over the environment. And in the end, these are all siloed. And that will give you a couple of examples of those vendors in that place. They're doing great things, but they're good at something, but they will never give you that complete picture, right? They all cover a part of that environment. And that typically results in incomplete dashboards. And this is where the root cause analysis story comes in. And I will talk about one of my use cases of one of our customers which had this situation. We already heard the word war rooms. Whenever things really go wrong, people typically are gathering together. All those different areas are asked to come into the war room. We need a network specialist, we need a database specialist, we need a cloud specialist. And then they all going to look through their own dashboards. And then kind of manually or in their heads try to correlate that. And that's really cumbersome. And what I also see happening, a lot of my prospects is just, yeah, we'll just add another monitoring tool that will give me better results. But adding another monitoring tool will not get you out of that level 2 observability. It will just increase the complexity, basically. So this will lead typically to slow root cause identification, inefficient war rooms, because in the end maybe 20 people show up, and when you're done with your post-mortem, it appears that only 3 people who should have been there, the other 70 are just, yeah, they looked at their stuff, but it was not in their area where the problem actually initiated. It also typically has the tendency of being pretty reactive instead of proactive, and the problem with linking IT issues to business impact. And last but not least, alert storms, because all those separate monitoring tools typically will send out their individual alerts. Not correlated, and then you're nothing as well. Typically not correlated, that you kind of rely on some correlation engine technology that is correlating all those different alerts together. What I think is what is missing in this specific approach is actually time series topology. And topology is kind of a digital map of your full stack, and kind of ties all those siloed pieces of information together. So you collect the data, you need to integrate it, enrich it, apply some analytics on top of them, and then come up with some actionable output on that one. And this is actually where StackState comes around the corner. We have built a solution that is actually topology powered, as we call that. And not only topology, which I mentioned as a missing link, but also the ability to track changes over time. And that's an important one, keep that in mind. So topology, what is it? Well, again, kind of a map that's showing you the dependencies, and we think that's really the foundation of your root cause analysis. What we typically see happening is that, well, things go wrong, you got all different alerts. Just as a very simple example, if we got a component over here that's not related to that one, they both are in red. Without topology, you kind of have to know they are not related. With topology, you can say, I don't have to look at that one because it's not physically or logically related to that specific one. So it's the foundation for root cause analysis. Why does it matter? Well, in the end, this reliability is the result of the interaction between all those components, whether those are microservices, containers, EC2 instances, databases, Lambda functions, S3 buckets, you name it. In the end, all the interaction between those components is what your digital product or your core value proposition is actually built upon, right? And then the relationship between these components also change very rapidly in a dynamic environment. Their load is increasing, your Kubernetes will automatically deploy some new pods with new containers, means traffic is also directed to that container, so it's extremely dynamic. And we talked about it a lot of times already. The change actually can cause an unanticipated consequence somewhere else in the stack. Again, a quote from Gartner, and I'm sorry Brandon, it's Gartner, it might be a competition, don't worry about it. But the context is actually topology. So the contextualization is something that we have been missing in the observability and or monitoring space until now. Why is it hard? Because it sounds so simple, right? And we all know that a lot of people already tried it. I worked for IBM a lot of years, and I was selling this stuff 10 years ago to my customers, what was called business service management, which kind of relied on the CMDB to give you a topological insight. But that miserably failed as well, obviously, because we all know they're never up to date. They're really hard to maintain. A lot of manual work is involved, and especially moving to the more dynamic environments, forget it. A container might live for only 100 milliseconds. Do you really want to manually register that in the CMDB when it goes away as well? So it's really hard because you have to look at all the fragmented of the puzzle. All these different pieces of technology, they know about topology. They know maybe about the application. Dynatrace, for example, perfectly knows the application stack. There's no need to add additional tooling for that one. But your network environment might not be monitored by Dynatrace, but maybe something like SolarWinds can understand which switch is talking to which router. Like AWS understands its own components and how they're related to one another. So what we actually have built is a version graph database when we started StackState in 2015, which was really, really tough. Graph databases obviously are the most suitable technology to kind of start reasoning about topology, how relations and components, but we wanted to make it versioned, and we are able now to actually update let's say the incremental changes up to the millisecond. So it means if a version change takes place from 3.7 to 3.8, that's an incremental update. And we store that as an incremental, very tiny bit of data in our version graph database. So we made that graph database actually behaving like a time series database. So a combination of that one. And believe me, it took us 3 years to build that database. And also one nice, maybe effect is that Google, in one of their chapters in their site reliability engineering practices, they literally say, do not attempt to build your own graph database versions, because we tried it and we failed. And then my founders actually thought, well, if Google can do it, then somebody has to. So quick preview and how does this look like? Well, this is just an example of such a topology overview where you see some business services and immediately understand which component actually caused the problem. In this case, the database. Problems are automatically grouped, and bear in mind, these components typically are monitored by multiple monitoring tools. This could be an alert from Nagios, this could be an alert from Dynatrace, could be coming from App Dynamics, come from whatever you want. So all these levels of telemetry on top of the topology, that topology is then the key to correlate all these things together. And then again, this is another example of a cloud native environment where we look at Kubernetes running on AWS, where we see an anomaly detected on the orders process, again, grouped automatically together. And then the next thing, the timeline at the bottom. So we made the time traveling. That's that version part of the graph database. So you're not only looking at the current state of the stack, but also the ability to look how it looked back in time. Not only from a topology perspective, but also from a telemetry perspective. Last but not least, it's still symptoms. We detect an anomaly, like the one I mentioned before. I don't agree that CPU utilization actually was identified as the cause. I'd like to understand what caused that problem. And this is again where we then go and take a little dive deeper, where we actually show the probable causes and list out everything that changed in the environment. Could be a configuration change, could be a topological change, could be a health state change, etc., etc. And in this specific example, we actually go to look and we see that some of the version update took place, and then we can, because of the version graph database, you can pretty much not see it very well, but apparently there was a security rule in AWS that did not exist anymore. So that version change also included some configuration change. So the AWS security rule, which allows the order process to connect to the Mongo database, actually got removed. So this is a perfect example of a change that occurs somewhere in the stack, which actually impacts the Kubernetes of the application managed by Kubernetes. And again, so topology together with telemetry, the ability to actually add all those changes on top of that is my vision of doing proper root cause analysis. Then let's talk about one of our customer use cases, which we mentioned in the content that we shared with you. It's actually NN Bank. It's a bank in the Netherlands. They are retail bank, investor bank, insurances, etc., etc. And they are actually one of our first customers. They had the same challenge as everybody had back then. Fragmented silo pieces of information. The solution they chose back then for that was Splunk. So they already did a lot of work by collecting all the data, at least breaking down those silos and bringing that together in one data lake. However, they still had very bad customer experience. The Net Promoter Score was 6.6, and that's not good enough for such a customer. Also, the availability was poor, only 97.57%. And they had a lot of data at Splunk, but their mean time to repair was still pretty bad. What they actually said, and this is Sander Vijfgracht, the chapter lead of the testing and monitoring department, he said, and this is a nice quote, "We saw the cause, we saw the problem, but we did not see how they were related." So all these, it's again, the data is not the problem. It's the correlation that is the problem. The data was there. They had monitored that there was a change. They knew there were problems in the end user perspective. But what they were really lacking, again, is that correlation or contextualization. And with that, it's his quote, it's not mine. He said we were able to reduce the mean time to repair from 24 hours to 1 hour. And why is that? Because initially you could think, yeah, but Splunk can do the same, right? I mean, it got all the data. It's just a matter of searching for the right input, right content, using the so-called saved queries. However, those saved queries are a great tool if you know what you're looking for. Then you can get information out of that. That's amazing. Splunk is one of the amazing tools I've ever seen, right? But it's also very amazing when you know what you're looking for. Well, the thing is, you want to do root cause analysis, you typically don't know what you're looking for. So they were building out saved queries that consist out of 600 lines of codes to try to figure that problem, figure out that problem. And again, with the correlation of stacks, and on top of that, we kind of automatically provided them for them. This one I already talked about, Vodafone GigaTV, where again, they really focus on customer happiness, like you already said, net promoter score, customer satisfaction, but also an important KPI for them was to reduce the customer calls, because every customer call costs you a certain amount of money. With StackState on top, we actually visualize their in-house built application, their streaming television. You have to imagine a complete subsystem set that kind of downloads movies from Walt Disney, download movies from this movie provider, then get the description of that movie from a different website, get trailers from another one, combine that together, and then provide that to the end customer. Or things like replay TV, where you as a customer want to see the news not at 8 o'clock in the evening, you want to watch the news of the morning. So those channels need to be recorded and need to be replayed as well. And there were a lot of problems over there as well. And also here again, their quote was, we reduced the mean time to repair from several days to several minutes. And I got another one, but I don't want to brag too much. So let's keep it to this, if that's okay with you. Does this make sense?
Yeah. How do you get the data into the database?
Yeah, obviously that was the biggest challenge, right? I mean, we all know when we tried this before, how do we deal with different naming conventions? How do I understand that this component and this technology is actually the same component as in that one, but here we use, I don't know, host name. Here we use IP address. Or maybe the CMDB has PROD underscore before the host name to distinguish production and acceptance. Yeah, we created, I already mentioned that version graph database, that was kind of the foundation, but on top of that we have created a very flexible ingestion engine. We call it a synchronization pipeline, actually kind of getting that raw data in, typically pull that from the APIs of the original tooling, like talking to ServiceNow to get static information in, talking to Kubernetes directly, talking to AWS, talking to Dynatrace, and then this ETL process takes place. So extract, transform, and load. And obviously we have incorporated the technology to automatically merge and deduplicate it. So we kind of tackled that naming convention problem, I would say with 99.99%. Sometimes you will still have discrepancies in data. That's always the case, by the way, typically. For that, we have some prioritization technology in place that kind of gives you automatically the right choice. Like, there's discrepancy in data between the CMDB and what Dynatrace is mentioning. Then it's a no-brainer, right? Dynatrace is right, because it's a real-time monitor. For example, it's a different IP address, then we will keep the data from the original source, but we say, well, we prefer this one over this one. And that was really the challenge that we actually took. So the reason behind that, and I really fully support that vision, there will be never one tool that will give you everything. But all these tools, they provide a great deal of value in their own part of the world. So instead of reinventing technology, we kind of came up with the idea, let's take a step back and think about which types of technology knows about topology. And then we actually came up with 5 different types of data sources. You can look at your administrative data sources, like a CMDB, or an Excel sheet for my sake, doesn't really matter, fine. However, some value in it, but not really accurate, like we discussed before. The second one, you can look at your CI/CD pipeline tooling, your deployment mechanism. If you just deployed some, I don't know, an application or let's say a web server on a compute node, then that deployment mechanism knows about the relations between those two. Another piece of the puzzle. Third technology we can look at is tracing technologies, like Dynatrace, New Relic, AppDynamics, but also things like network tracing, SIP tracing, whatever type of tracing there is. Again, a piece of the puzzle. Then the fourth type of technology we can look at is the so-called service registries or service provider, like AWS or VMware vSphere is also a very nice example. They know exactly which virtual machine runs on which ESX server. And the fifth technology we could have a look at is the discovery technologies. They're not that well commonly used anymore, but let's say 10 years ago we had things like application dependency discovery technologies. But in the end, these are the 5 types of data sources, and there's obviously a lot of different vendors in those different types of data sources that understand that little piece of the puzzle. And what we've built is actually get that data together and then automatically merge and deduplicate that in one unified view. And then the same technology is actually used to get the information of the telemetry from all the different data sources. Like I showed you, we got cloud monitoring, we got network monitoring. We don't copy that data, we actually use streaming technology to kind of automatically say, oh, this is a container, it's monitored by Prometheus. So we connect to Prometheus and automatically plot the telemetry, all the metric streams, and if we already configured the alerts, the health states, etc. on top of that component. And then the component on top of that might be, a application, it's monitored by Dynatrace. Same idea, we get the telemetry, like response time from Dynatrace. So we layer all those levels of telemetry on top of the topology, and this is where the correlation actually takes place. But there's a lot of more to cover, and my time is pretty much running out of time, I think.
Keep going.
Yeah?
You're all good. Yeah. We started back here, so we've got an extra 15 minutes.
Oh, great, I love that.
Don't use it all.
So,
We've got a guy Zoom.
more questions or remarks, or maybe things you don't believe.
Yeah.
So maybe continuing on that one then, I see a lot of the, especially observability vendors, they're moving into that space. New Relic
Yeah.
is starting to do topology, I've seen it
Yeah.
in their product. So what's the differentiator?
Yeah. Especially Dynatrace is getting close, I believe. They are really invested a lot. The thing is, like I said before, I personally don't believe that one tool will do it all for you. I mean, especially in our DevOps environments, you got teams that are completely autonomous. They choose Prometheus. They don't care about that the management will tell them, you have to use Dynatrace. So with those autonomous teams, you typically see, again, growth of different technologies. So all these different technologies, they have their limitations. And that's why we actually said we don't invent new technology at itself, but kind of reuse that existing one. Second big differentiator, but that's a different story, is pricing. I mean, I see a lot of companies like Dynatrace, if you want to deploy it in your complete environment, I've never seen one doing so. You have to pay I don't want to use the word, a lot of money.
I assume a lot of your, so a lot of it is the raw data input, but it obviously has to have a context. Is there an aspect of consultancy with a client that has to describe those services? You mentioned the topology.
Yeah.
Obviously, this has to be constructed in some form of a service model to understand where the failure point
Yes.
is, what the impact of
Yeah.
the service is. Yeah.
Good question. We focused on building the platform. We didn't want to be a system integrator because it's impossible to catch up with 40 years of IT technology, right? It should mean that we would become an integrated company, or having that, one of our advisors calls it, the hell of compatibility. So what we've did is, as soon as we had that platform finished, we kind of developed a couple of out-of-the-box integration for the most usual suspects, like ServiceNow, AWS, Azure, Kubernetes, VMware. But just as a nice example, when we went to one of the insurance companies in Switzerland 3 years ago, their main monitoring tool was Dynatrace, and we didn't have an integration for it yet. So obviously we thought about that by developing a kind of, call it this SDK, software development kit, where together with their domain expert, just like you just said, you have to kind of translate that ETL process, right? You have to understand what components are known in there, how do I recognize them, and how do I then transfer them into that grid that I just showed you over here as an example. Like, that topology, like this one, for example. I think this is more easy to use as an explanation. Like, how do I know this is a web server and it should belong to the application layer? So making that integration with Dynatrace together with one of their experts took us 3 weeks. We worked with the Turkish bank this summer. We integrated Dynatrace, F5 Big IP, Rancher, SolarWinds, but it was still limited to the technology stack. When they really got the idea, it was a proof of concept, but that we finished in 2 weeks only, so that was really quick. When they realized what the capabilities of StackState were, they actually said, well, I like this because now at least I see, from a Dynatrace perspective, I know which processes are running. Rancher knows which containers are running, but Rancher, for example, doesn't know which processes are running in Dynatrace. So that was stitching those technology pieces together. But then they said, but we, at the bank, we have very important data about the actual business. They talk in terminology like operation codes, function codes, and application code, which was actually the layers on top of the technology. And they had that data, they captured that data, really a lot of data, in Oracle database. So this is again an example. We say, okay, now show me that data. Let's see if we can translate that in this 40 data model concept. And then we really are starting really value because we were relating business topology to the technology topology. Because integrating technology by itself doesn't provide real value. You really have to tie it back to what the business and also be able to kind of talk their language. Does that answer your question?
Yeah, there was like the example you gave was a failed change. So you mentioned as an integration to say IT service management platforms like ServiceNow.
Yeah.
You can detect not just the fact that there was a change, but what change it was. You know, what was the actual change request.
Yeah, for example, those changes in ServiceNow was actually one of the first with that Swiss insurance company as well, where we incorporated the involvement of the change request from ServiceNow. So we say, hey, change request has been requested, it has been approved, and it has been carried out.
So no alert, yeah.
That was one of the first things. But typically, and that's the good news with going to more modern technologies like Kubernetes and AWS, we all know with change request, it's only approved when it's manually said it's approved, right? Then it can still be in a couple of hours later than the actual request took place. But with modern technologies like you deploy some new Helm chart, that's known by the deployment mechanism behind Kubernetes, and that's a real-time change that we also capture as a real-time change. Or the example I gave you where the security rule got thrown away, that we see all these things as properties of the components. So all these components have different properties. Could be its health state, but could also be who's responsible for it, just metadata. Could be what's the current version. What's the current, I don't know, jar file behind it, and you name it. We attach them as properties, and as soon as one of these properties changes in the tools that we integrate with, we near real-time reflect that as that change on the version graph database.